Okay, I'm just going to go through the force analysis for the midterm project. Let's see if the light makes that any better. I don't know if that helps or not. Okay, so we are going to look at a golf ball, and we're going to consider different forces, right? So we're going to have gravity, and then we will have the effect of spin, so the Magnus force. And then we're going to have air resistance. And we're going to add some gusts of wind in there too. And those will go together, air resistance and wind. Okay, so let's look at our free body diagram, what that might look like. So remember, just to get our picture of what's happening, this is the tee where the person's going to be standing and swinging the golf club. And then way down over here will be the hole. And this is like 155 yards. And our direction, we are calling this X. This is Y. And coming out of the board or out of the page is Z. Okay. So as the ball is in flight, we just kind of draw our free body diagram. Assume, let's say, the motion is in this direction. We don't put velocities on our free body diagram. But we are going to have the force of gravity. And we're only going to look at the case of backspin. So this means as the ball is going this way, it's spinning backwards like this way. So, if we just freeze the ball for a second, it's spinning that way. If we do our right-hand rule, put our fingers in the direction of rotation, our thumb shows the direction of the angular velocity. So omega is just omega k hat. It's only in the z direction. Okay, so we have, so as this ball is moving, we have gravity course is always pointing down. We're going to have air resistance that'll be in the opposite direction of the velocity. And then we are going to have this interaction from the Magnus force. So Fm is some constant that depends on the object that's moving, and it's omega crossed with V. So we went through this in class of the, using this right-hand rule. So this is our fingers go in the direction of omega, and then we curl into V, and our thumb will show us the direction. So if we do, I don't know if I could do it under the, nothing's going to fit under there. I have a candle. How about that? So this is going to be the direction of omega, and then we're going to curl into the direction of V like that. And so our thumb will be in this direction. So the lift in this particular direction for the Magnus force is in that direction. Okay, so we want to then sum the forces, because what we're trying to do is get an acceleration, and once we have an acceleration, we can apply the Euler method. Okay, so some of the forces, we have force of gravity, we have force of drag, and I'm just writing pluses here because I'm putting vectors on top, right? So I'm going to take direction and components into account in a second. And then the Magnus force. Okay, so we can now break these out into their component forces. And we're going to do 3 dimensions here, right? Because we have a x, y, and z. So force of gravity, right? If we just look at our coordinate system again, x, y, those are our positive directions, and plus z here. Okay, so gravity is in the negative y. G, it has 0 in x and 0 in z. My drag is going to have a component that is in the x and the y based on this velocity. But it could actually have a component in any direction, because we'll see with our gusting wind, we may actually have z components as well. So that's going to be, and let's just go through that again, because I think I didn't do it quite right in lab, but let's say this is our drag force, okay? And we know that our drag force is negative b2 v squared. Now we want to know what is the x component and the y component. I probably should draw it this way, right? Because based on how my velocity is there. Okay, so we're going down and then left. Okay, so this is theta, the angle that it's moving at, right? And this would be my f drag x and f drag y. Okay, so f drag x equals, so my f drag, right, the magnitude times cos theta. And we can look at cos theta. This angle is the same as what's happening for the velocity. So that's my velocity, and this is Vx, and this is Vy. Same angle, right? Because drag always just opposes velocity. So then cos theta is Vx over V. So let's substitute that in over here. So we get Vx over V, and then we substitute this in here for my drag. So negative B2 V squared. And so that will simplify to give us negative B2 V. So this is the magnitude of the velocity. And then, right, that V squared cancels that, and I just get Vx. So that's the easier way that we were doing in the other labs. Okay, so then if we go back up here, my drag force is negative B2, the magnitude of velocity times the x component of velocity, negative B2 magnitude of velocity times the y component, B2 magnitude of velocity times the z component of velocity. This will be 0 to start out with, but it won't always be 0. Okay, and then I want to do the Magnus force here. So what are these components that are going to go in here? So we have to work out that cross product. So let's just look at omega cross v, right? Because we know that the Magnus force is S0 omega cross v. Okay, so if we just want to do that cross product, right, we write out our vectors with the unit vectors. So we have I, J, K, and then we get the Wx, Wy, Wz, so the components of our angular velocity, and then the components of our linear velocity, Vx, Vy, Vz. Okay, and now we take the cross product of that. So we do, so remember, if we want to get like the I hat direction, we block this out and we do these two minus these two. So it's I hat omega y Vz minus omega z Vy. Okay, and then the j hat, we do these, but remember there's a minus sign in front of the j hat. And then we do omega x Vz minus omega z Vx. And then k hat, we get omega x Vy minus omega y Vx. Okay, so if we go back over here, remember we said that our angular velocity is only in the k direction. So omega x and omega y equals 0. So if we go over here and get rid of all the terms that have, oops, let me get a little twisted here. Get rid of all the terms that have omega x and y. Sorry, I have more camera problems. Okay, so omega y, that goes away. Omega x goes away. We get x and omega y. So what we're left with is, in the I hat direction, we have negative, let's do it the other way. Negative omega z Vy I hat. And then we have the negative here and a negative here. So it's plus omega z Vx j hat. And I said before that we only have a z component, so we can just rewrite omega z as omega. It is the same as the magnitude. I hat plus omega Vx j hat. That's omega cross V. And then, so the force would be S times that. So if we go back to our summing the forces, so we have 0 minus Fg, 0 for gravity. We have our drag, B2 V Vx, B2 V Vy, B2 V Vz. And then we have our Magnus force, which is just going to have the x and y component. So it has negative omega Vy and omega Vx and 0 in the z. So last thing to do is just add in wind. And that's really just going to affect this term in the wind. Okay, so to incorporate wind, if we just look, for example, at the drag in the x direction, B2 V Vx. So basically, this is the magnitude of our speed, right? Or it is our speed, the magnitude of our velocity, and this is the x component of the velocity. So when we have wind, these are going to change, and this is going to be the magnitude of our velocity minus the wind, right? So it's really our relative velocity, our velocity relative to the air, and then this is going to be Vx minus V wind x. Okay. So how do we calculate this? So it's saying take the difference in my velocity minus my wind, right? So that's really like a Vx, Vy, Vz minus V wind x, V wind y, and V wind z. Okay, and then I want to take the magnitude of it, right? So the magnitude is going to be the square root of x squared plus y squared plus z squared. So the magnitude of V minus V wind is the square root, or you can use the norm function, Vx minus V wind x squared plus Vy minus V wind y squared, Vz minus V wind z squared. So I'm going to give you a function that, for every step of your Euler equation, it's going to give you the V wind vector, and then you'll compute this. Okay, so if we had, I guess we have enough now to write out, let's do, for example, the y component of the force, right? So this is over here, right? This is really some of the forces in the x, some of the forces in the y, and some of the forces in the z. So let's just do the x equation or the y equation as an example. So we have the negative force of gravity. We have our air resistance term, so that's going to be negative B2 V minus V wind, which again we're going to calculate like that, and then Vy minus V wind y, and then I have to add in, oops, you guys didn't correct me here, I forgot my S0 term, S0. Okay, so in the y we have plus S0 omega Vx. Okay, and if we do the sum in the x direction, I guess just for completeness, I don't know why I did them in order. So it'll be negative B2 V minus V wind Vx minus V wind x minus S0 omega Vy. And so when I'm saying V here, this is really the velocity of the ball, right? X velocity of the ball, and this is at that particular step what the wind is going to be. And again, I have a function that will give you that. And then finally, the Z component is just going to be the air resistance term, so negative V2, V minus V wind, Vz minus V wind, Z. And that's it. And then so the next step now is to figure out how to get this into kind of a pseudocode expression. And yeah, and for the rotation, we're saying omega starts in the Z direction with backspin, and it is always staying in there. Omega is never changing direction.